Scientists rejected atoms for 100 years. Not fringe scientists, not flat earthers hiding in basements. The most respected physicists and chemists in the world looked at the evidence for atomic theory and said no. For a century, the idea that matter is made of tiny, indivisible particles was treated as philosophy, as metaphor, as something a scientist shouldn't waste time on. And here's the thing that should bother you. They weren't being stupid. They had a reason. A coherent, philosophically serious reason for rejecting atomic theory. And understanding that reason is the only way to understand how science actually works. This is no science. And this is the story of how the invisible became undeniable. The story starts where most science stories do, with someone who was right for completely the wrong reasons. Around 450 BCE, a Greek philosopher named Leucippus proposed an idea. His student, Democritus, developed it further. They called it the atomos, the uncuttable thing. The argument went like this. If you keep cutting matter in half, you must eventually reach something that cannot be cut. Something fundamental. Something indivisible. It's an elegant idea, and it sounds like the birth of atomic theory. But here's what the textbooks often skip. Democritus had no experiments, no measurements, no way to test his claim. He arrived at the atom through logic alone. Pure philosophical reasoning about what must be true. That's not science. That's an inspired guess. And for 2,000 years, it stayed a guess. Aristotle rejected it. The church largely ignored it. The idea floated through history like a rumor, compelling but untethered. The Greeks didn't discover atoms. They imagined them. And imagining something, even correctly, is not the same as proving it. That distinction matters, because it took 2,000 more years and a very different kind of thinker to start building the real case. The first person to give atoms a fighting chance wasn't a philosopher. He was a Quaker schoolteacher from Manchester who was obsessed with weather. His name was John Dalton, and he didn't start with atoms. He started with gases. But Dalton was building on something crucial that had happened 20 years earlier in Paris. Antoine Lavoisier had done something that sounds simple but was revolutionary. He weighed things. Before and after chemical reactions, precisely. And every single time, the total mass before the reaction equaled the total mass after. Matter wasn't being created or destroyed, it was being rearranged. Then Joseph Proust added another piece. In 1799, he showed that elements always combine in the same fixed ratios. Water is always 8 parts oxygen to 1 part hydrogen by mass. Always. Not approximately. Always. Dalton looked at these patterns and asked, what kind of matter would behave this way? Between 1803 and 1808, Dalton developed and published his atomic hypothesis in A New System of Chemical Philosophy, proposing that discrete particles, each element with a characteristic mass, could explain these patterns. Chemical reactions are just atoms rearranging in fixed numerical ratios. That's why the proportions are always the same. That's why mass is conserved. It was the first time atoms weren't just a philosophical position. They were an explanation, something that made precise, testable predictions. And the scientific community looked at all of this and largely said, interesting, but not proven. Which brings us to the part of the story that science education almost never tells you. Here is what's easy to assume, that the scientists who rejected atomic theory were simply behind the times. Stubborn old men clinging to outdated ideas. That assumption is wrong. Ernst Mach was not a fool. He was one of the sharpest minds in European physics. The unit of sound speed, the Mach number, is named after him. Einstein called him an influence. And in 1897, Mach expressed his skepticism about atomic reality before the Imperial Academy of Sciences in Vienna, arguing with full philosophical conviction that atoms, as physical objects, could not be directly observed and therefore could not be claimed to exist. His argument wasn't ignorance, it was philosophy. Mach belonged to a tradition called positivism, the idea that science should only deal with what can be directly observed and measured. Atoms, by definition, were too small to see. No microscope could reveal them. No instrument could detect a single one. So for Mach, atomic theory wasn't wrong exactly, it was meaningless. A useful calculating tool, maybe, but not a claim about physical reality. Wilhelm Ostwald, who would later win the Nobel Prize in Chemistry, championed energetics as an alternative to atomic theory. He argued that energy, not discrete matter, was the fundamental substance of the universe, and that atoms were therefore unnecessary to explain chemical phenomena. And here's the uncomfortable truth. Given what they could actually observe in 1897, they weren't being unreasonable. Dalton's atomic theory explained the chemical patterns beautifully. But explaining a pattern isn't the same as proving the mechanism behind it. You could, in principle, explain fixed proportions without invoking invisible particles at all. Science has a name for this problem. It's called underdetermination. Multiple different theories can explain the same evidence. The evidence alone doesn't tell you which theory is physically real. To break that deadlock, you needed something more. Not just a theory that fit the data, a theory that made a new, specific, quantitative prediction. One that could be tested and falsified. That's exactly what arrived, from the most unexpected direction. In 1827, a Scottish botanist named Robert Brown was looking through a microscope at pollen grains suspended in water. The grains were moving, jittering, randomly, constantly, with no apparent cause. Brown ruled out currents, vibration, and living motion. The pollen was dead. The water was still. And yet the particles never stopped moving. For nearly 80 years, nobody had a satisfying explanation. The phenomenon carried Brown's name, Brownian motion, but its cause remained mysterious. Then, in 1905, a 26-year-old patent clerk in Bern published 5 papers that would reshape physics. One of them was about Brownian motion. Albert Einstein had never conducted an experiment on Brownian motion. He worked entirely from theory. His argument was this: if matter is made of atoms, and those atoms are in constant thermal motion, then they should be constantly bombarding anything suspended in a liquid. A pollen grain, for instance, would be hit from all sides by millions of water molecules every second. Most of those collisions would cancel out, but statistically, at any given moment, slightly more hits would come from one side than another. The result? A random push. Then another. Then another. That's Brownian motion. Not a mystery, a statistical consequence of atomic reality. But Einstein didn't stop at the qualitative explanation. He derived a precise mathematical formula predicting exactly how far a particle should travel in a given time, based on temperature, viscosity, and, critically, the size of the atoms doing the hitting. This was the key. Because if you measured the actual displacement of real particles and plugged those numbers into Einstein's formula, you could calculate the number of atoms in a given amount of substance. Avogadro's number, the number of atoms in 1 mole of any substance. The fundamental constant that links the atomic world to the measurable world. Einstein had given science a bridge. A mathematical bridge from something you could see, a jittering pollen grain, to something you couldn't, an atom. But a mathematical prediction isn't proof. Someone had to go into the laboratory and check the numbers. Jean Perrin was a French physicist who had been thinking about Brownian motion for years. When Einstein's 1905 paper appeared, Perrin recognized it immediately for what it was: a testable prediction. A set of specific numbers that either matched reality or didn't. Between 1908 and 1913, Perrin conducted a series of extraordinarily careful experiments. He prepared suspensions of tiny resin particles, gamboge, ground to uniform size. He tracked their motion under a microscope. He measured their displacements. And the number that came out? 6.02 times 10 to the 23rd. Avogadro's number, calculated from watching dust move in water. Perrin didn't just get one result. He calculated Avogadro's number using multiple completely different experimental methods: Brownian motion, sedimentation equilibrium, critical opalescence. Every method gave the same answer. When completely different experimental approaches converge on the same precise number, that's not coincidence. That's reality. Wilhelm Ostwald, who had championed energetics as an alternative to atomic theory, reconsidered his position after reading Perrin's results. In 1908-1909, he acknowledged that the evidence for atoms had become compelling. He wrote that the atomic hypothesis had now been proven beyond reasonable doubt. Ernst Mach never fully converted, but the field moved without him. Perrin received the Nobel Prize in Physics in 1926, specifically for his work on the discontinuous structure of matter, which is the formal way of saying, for proving atoms are real. Here's what strikes me about this story. The atoms were always there. The patterns were always there. Lavoisier's scales, Proust's ratios, Dalton's diagrams, all of it pointed in the same direction. But Mach and Ostwald weren't wrong to demand more. They were right to ask, how do you know it's real and not just a useful mathematical fiction? The answer, when it finally came, wasn't a bigger telescope or a more powerful microscope. It was a mathematical bridge. Einstein's equations connected the invisible to the visible. Perrin walked across that bridge and came back with a number. The lesson here isn't that skeptics are obstacles to progress. The lesson is that science doesn't accept truth by consensus or by elegance. It accepts truth when a theory makes a specific, quantitative prediction, and reality matches. 100 years of resistance ended not with the discovery of atoms, but with a calculation so precise, so independently confirmed, that disbelief became philosophically untenable. This story reminds us that the most powerful scientific arguments aren't the ones that show you something new. They're the ones that make the invisible count. But atoms aren't the only thing science resisted for a century. There are other ideas sitting in the textbooks right now that we accept without asking how we actually know. I'm here to help you know how evidence changes what we believe. What other scientific idea do you think deserves a closer look? Tell me in the comments. See you at the next experiment.